worked with Dr. Namakundu for my project using waste-based alternatives for sustainable construction materials. So this is my table of contents, my abstract, my methods and materials, geopolymer, concrete, mycelium, and seaweed, which are the three materials I explored as alternatives. So my topic was based on waste-based alternatives. So the construction industry accounts for millions of tons of CO2 emissions annually, and it has a wide range of negative consequences like industrial runoff, toxic byproducts, and depletion of natural resources. It can also cause global warming, melting glaciers, and damaging natural ecosystems and polluting the air which humans breathe. But these can be reduced by using substitutes for traditional construction materials. Concrete is generally made from Portland cement, which is basically like crushed granite. But this crushed granite generates a lot of CO2 because it's an organic compound, which means it contains carbon, and it also uses a lot of water. So there are alternatives to use waste with high amounts of inorganic compounds, which means compounds with aluminum and silicon that don't have carbon. So they can be used as an alternative so as to generate less CO2. The methods and materials, I did a literature review using electronic research. These were the websites that I used. And my inclusion criteria was basically talking about any of the materials that I was interested in exploring. And geopolymer concrete. Concrete is made of cement paste, which is cement and water, and crushed sand aggregates, generally made of stone, which can be very wasteful, as I talked about in my introduction. But geopolymer concrete is an alternative. It's made of aluminosilicate chains and combined with an alkali activator, which is generally sodium or potassium ions. And this mixture is then combined with water and cured at a particular heat or maintained at specific heat and moisture level to gain strength. And the concrete is then used in precast structures or whichever the construction application is made. The alternative materials for concrete in general include clay and clay minerals, laterite soil, which is corrosion resistant, fly ash, or the ash remaining when coal is burned, blast furnace slag, which is left behind when metal is separated from ore, and red mud, which is like also a type of construction material. It's when bauxite is mixed with sodium hydroxide and heated under pressure to produce aluminum, and most importantly, plastic pellets, because there's a lot of marine plastic pollution and plastic accumulating in landfills, which doesn't biodegrade, which is why all of these materials can be crushed into fine sand aggregates and used as a replacement using alkali activators. The properties of geopolymer concrete are that it is sulfuric acid corrosion resistant, which means generally because of acid rain, when in areas with factories with high pollution and byproducts, sulfur dioxide is emitted into the air, and the sulfur dioxide reacts with water in the atmosphere to form sulfuric acid, which then reaches Earth as acid precipitation. But this causes like typical buildings made of cement and traditional concrete to erode. It strips off the surface and it causes the structure to deform. But geopolymer concrete is resistant to that. It doesn't get damaged by sulfuric acid, which means that it can be used in areas with high industrial runoff and sulfur dioxide emissions. It has decreased CO2 emissions, like I mentioned earlier, because of its lack of organic compounds. It has higher compressive and tensile strength, which means that it can resist compression and tension better. And it has a quick setting time, which makes it better for using in precast structures, which are basically like structures that are cast separately and then imported into a construction site to save time. The applications include 3D printing houses, making precast structures and used in areas with high plastic waste in landfills. The way you 3D print houses is basically a 3D printer mixes the materials together and stores them in a silo, and then uses that material to pump out houses layer by layer. And finally, the printed structure is like a template for the house where it costs less, it's generated faster, It doesn't require as much labor, and then HVAC systems and ventilation are installed manually afterward. And they're also very cheap, so they can be used for low-income families. The second material I investigated was mycelium, which is basically mushroom root. Um, mushroom root mycelia are thin filament-like fibers that grow very quickly, and they're also very durable and strong. The way they're grown is basically organic matter is collected into a container, and mycelium is put on top of it, and the container is closed. A few weeks later, a few days to a few weeks, depending on how much organic matter there is to decompose, the organic matter turns into mycelium blocks, which is like firm and rigid. And these blocks can then be used for construction. The properties of mycelium include its lightweight nature, so it doesn't weigh as much. It doesn't cause structures to break because of heavy loads like concrete does. It has a very low production time. All you have to do is put organic matter in some mycelium and grow it. Takes a few days to a few weeks. And it also requires minimum capital. And these are examples of structures that have been constructed with mycelium. One is the growing pavilion in the Netherlands, where it's literally like a growing pavilion, like it continually grows as the mycelium is like attached inside. And it's an example of how mycelium can be used in construction material in the future. This is also the Hi-Fi Tower in New York City, and another mycelium-based structure that shows the structural strength, where this one mycelium center can support the weight of the entire roof of the building. And the future applications are, first of all, construction, towers, pavilions, low-rise structures, but it can also be used for clothing. It can create soft and durable material, which is an alternative for leather, which also generates a lot of heavy industrial runoff and animal slaughter. It can also be used for the packaging industry as a biodegradable alternative to styrofoam, as you can see in the images below. The final material investigated is sargassum seaweed. Sargassum is a stinky parasitic seaweed generated from high nutrient levels in water. It's kind of like an algal bloom, but like seaweed. And it grows quickly and it tangles people who step in it. And it washes ashore in large amounts and turns clear water into like murky brown content. Recently, it's grown a lot and washed into like a seaweed belt that washed ashore to Florida and Mexico. Um, the government generally pays people to collect these and then it burns them, or sometimes it can't figure out what to do with this excess seaweed. So instead, sargassum can be crushed and used to make durable brick, which is strong enough to build houses and resist weather fluctuations. And it can also be used as a substitute for traditional brick. In conclusion, geopolymer cement is made of construction waste and biomatter such as mycelium and seaweed, which are sustainable alternatives to traditional construction materials. They reduce carbon emissions, transport costs, and heavy metals that leach into the soil. They also increase insulation, fire resistance, sulfur resistance, water absorption, and compressive and tensile strength. Further investigation can include incorporation of additional properties such as resistance to mold, because mycelium is strong, but it still like molds when it's exposed to water. So finding an alternative for that is one option. Increasing rigidity, so they're more strong and can support like corporate buildings and skyscrapers maybe one day, and resistance to water or hygroscopicity. And experimenting with different production conditions, like the study that I conducted had very specific temperature conditions around 60 degrees Celsius for geopolymer concrete. So different temperature, moisture, and material ratios can be used to see which generates the strongest structures. And these materials can be implemented to decrease cost and 3D print affordable structures for underprivileged or homeless families, as well as used in areas with high amounts of industrial construction waste. And finally, thank you to my mentor, Dr. Christina, from the Research Institutes of Sweden. She was really patient and helped me explore this topic that I was really unfamiliar with, and I really enjoyed this project. And also thank you to the Talaria staff for giving me this opportunity.